Hello friends, subscribers and new viewers of this channel, and welcome to Control Engineering and Signal Processing tutorials. In this tutorial we explain how to define and perform operations on symbolic complex numbers in Python. To perform operations on symbolic complex numbers we use Python's SymPy library. We will explain how to obtain symbolic and analytic expressions that can be automatically embedded inside of Python functions. Motivation. In control theory and signal processing, it's often necessary to define and perform mathematical operations on complex numbers and complex functions. Consequently, it is of paramount importance to have a programming environment that can be used to verify the analytical computations. For example, in order to sketch a Nyquist plot, we would like to compute the real and imaginary parts of a sinusoidal transfer function. For example, a sinusoidal transfer function is given over here. It's obtained from the standard transfer function by substituting s by j omega. As you will learn in this video tutorial, we can easily compute symbolic expressions for the real and imaginary parts by using Python's SymPy library. The first step is to create a Python virtual environment and to install all the necessary packages. So let's do that. Click on Start and open a command prompt. Over here, I will navigate to my codes folder. If you don't have the codes folder, you can create one. And inside of this folder, I will create a new folder called Python Complex. Then I will navigate to this folder, and inside of this folder I'm going to create my Python virtual environment. To do that, I need to execute this command, Python with an option m, venv, which is a command for creating a virtual environment, and I will call my virtual environment simply as environment1. Then I'm going to execute a script inside of this folder, and the path to this script is actually environment1, which is this base folder. Then inside there is a scripts folder, and I will execute this file activate.bat, and as you can see my virtual environment is active. The next step is to install the necessary libraries. First of all, let's install SymPy. We can simply do that by typing pip install SymPy. This is the symbolic Python library, which is super powerful, and besides using it for complex numbers, you can also use it for real numbers. You can even write functions in analytical forms, and you can perform all sorts of analytic computations. Then I'm going to install NumPy, just in case if we want to perform some basic manipulations with numbers, and that's it. In this video tutorial, I will be using Spyder editor to edit my Python file. Consequently, I will click on Start and search for Spyder. You can easily install Spyder either as a standalone application, or you can install it inside of Anaconda. There are tons of tutorials online on how to install Spyder, and also on my video channel you also have a number of tutorials. Okay, I will close this temporary script. I will close this, and the first thing that I need to do is to make sure that I can execute Python scripts inside of my virtual environment. To do that, I need to set up my Spyder. So I need to click on Tools, Preferences, and over here I need to click on Python Interpreter, and I need to click, let me show you, I need to click over here to find the path to my Python Interpreter inside of my virtual environment. My virtual environment is located in Codes, Python Complex, Environment1, Scripts, and here it is. And I will click OK. Then over here I will see this error, either if I try to type here and execute something, or the error will appear by itself. Consequently, this is what I need to execute. So let me copy this command. You can see it over here. And I need to go to my prompt and I need to install these additional packages such that I can run my virtual environment inside of Spyder. And this will take maybe a few seconds. And that's it. Now I can go back to Spyder, I can close this console, I can restart the console, and now everything will be fine. For example, I can try to import over here SymPy. I will try import SymPy as SP, and let's see, will this thing work? And voila, it works perfectly. Before I start with explanations, I will first explain several things about Spyder. Namely, in Spyder, if you want to evaluate an expression, you can do it like this. So for example, over here I'm going to import numpy as np, and then over here I will define an array 1, 2, let's say 2, 3, 4. I will call this array as a, and let's say I want to say that b is 2 times a. Now, what I usually do to evaluate these expressions, I will simply select this, and then I will simply press F9. And in this way, this expression will be evaluated, and over here will be the result. Now, in this terminal, you can type A, and you can see the result B. This is very similar to MATLAB. Again, you simply select something, and you press F9, and this block will be executed. And another thing is that you can independently evaluate blocks. So for example, I can say B2 is 10 times B, and I can simply select this block and press F9, and you will be able to evaluate this block, and you will see the results. The first step that we need to learn is how to define complex numbers. How to define complex numbers symbolically. Okay, in SymPy, we define real symbolic variables like this. X, Y. X will be the real part and Y will be the imaginary part. Then I need to type sp.symbols. And over here I need to type this x, comma. You don't need comma, you can just do space. And then I need to specify that these two numbers are real. And let's evaluate this, and let's see what's written over here. Now if I type x over here, you'll see nice print for my x, and y, you'll see nice print for y. And that's why I like Spyder, since Spyder will be able to nicely print these expressions. You can also do this to get a more primitive print, and for y. However, I don't like this type of print. Spyder will nicely write these expressions. So let's now define our first complex number. I will call it z, and it's going to be equal to real part plus imaginary unit. We type it like this, sp.I multiplying y. And let's see our number now. Here it is. Looks beautiful. Let's start with computations. Conjugate of our original number. So let's learn how to do that. I will call the conjugate z underscore bar, and I will type z.conjugate, and now we will have our conjugate number. So if I type here z bar, you will see it. It's a conjugate complex number. Let's compute the magnitude. Very interesting. How to do that easily. So let me type a comment, magnitude over here. I simply need to type this. sp.abs, which is an absolute value of my number z, and I will get it. Let me see if I do this. Here it is. Square root of real squared plus imaginary squared. That's it. Simple as that. Of course, there is another way to compute the magnitude. We can simply compute the magnitude by multiplying z and z bar. So let's do that. Z bar multiplying z, and let's see what will happen. You can see that over here this expression is not being multiplied. So that's why we need to type sp.simplify, and then we need to type this. And let's see, voila, here it is. This is now x squared plus y squared. However, we need to do a few more things. Then we need to do, for example, something like this. QRT, and then over here, let's try this. Let's see what we will get. And here it is. Here's our magnitude. Looks beautiful. To get the argument of a complex number, you need to use the function arg. So we can simply type sp.arg, and then over here I will simply get the argument of my imaginary unit. So let's see what is the argument. Here it is. It's pi over 2. And of course you can get arguments of complex expressions. Okay, let's now perform some operations on complex numbers. For example, how to expand a polynomial. To do that, let's define our polynomial to be, for example, z, and let's do something like this: z squared plus 2 multiplying z plus, for example, 3. And let's type this. Expand sp.expand p, and let's see what will happen. And here it is, beautiful. Looks amazing. Next, let's learn how to extract real imaginary parts of our complex numbers. So, for that purpose, let's compute a division of z over z conjugate. So let's call this expression 2, and let's compute it. I will call the resulting expression z1, and I will type z over z bar. And let's see this second expression. Here it is. And let's say that we want to compute the real part. There are several ways to do that. The first approach is to simply type this: z1 dot as real imaginary. Okay, so this function will actually compute the real and imaginary part, and it will store it in a tuple, as you can see over here. Let's call the return value as result1, and you will see over here that result1 is actually a tuple. So let's extract the real part. So we can type this result1, and then we can simply access the first entry, and this is the real part. To get the imaginary part, we simply need to type this result 1, then 1, and we will get the imaginary part. Oops, I made an error here. Here I'm making a correction, and here it is. This is the imaginary part. Of course, there are several other ways to get the real imaginary parts. Let's do the second approach. The second approach is simply to type this. A real part, let's write it down, second approach. To get the real part, we need to do this. R1 will be sp.re. That's the name of the function, and we need to specify z1. Here it is. Now we will have the real part, and let's get the imaginary part is sp.im, and then over here we'll have z1 again, and let's see what we get. We get this. This is our imaginary part. Next, let's learn how to evaluate the expression at a certain point. To do that, we simply need to type this. Let me first write a comment, evaluate at a point. So for example, we want to evaluate a real part at a point. To do that, we simply need to type this, R1, and then we need to call the function evaluate f, and then we need to type subs, and over here inside of this dictionary we need to substitute the values. So let's specify the values. X will be 2, then y will be 2, or let's do 1. And let's see what's happening. Now, here it is. We are now evaluating the real part, that is this part, and if we substitute the values, we will get 0.6. We can do the same thing for the imaginary part, and we can just type this again, and let's see our imaginary part. The original expression is given over here, and that's it. Simple as that. Next, let's go back to the problem from the beginning of this video tutorial. Here's my sinusoidal transfer function, and I want to compute the real and imaginary part of this transfer function. So let's learn how to do that. First of all, I need to define a symbolic omega, which is my radial frequency. So let's type define a sinusoidal transfer function. And over here, I will first define my frequency. I will type SP, symbols, then over here, I will call this as W, and I will specify that this is a real number. Then let's define our transfer function. It looks like this: 1 over imaginary unit multiplying omega multiplying imaginary unit, or let's put it like this, 1 plus imaginary unit multiplying omega. And that's it. So let's see our expression. If I type t, here it is. Okay, let's now compute the real and imaginary parts. Again, let's type t. Real is sp.real t, and t imaginary is sp.imaginary t. And let's see our expressions. T real, and we can see over here t imaginary. And that's it. These are the expressions. Okay, that's all for today, and thanks for watching.